All right, good afternoon all. I'm Jeff Mendelson, I'm from Bloomberg. I'm a team lead there and I work in the software infrastructure group. Recently I was working with an intern. Actually, I'm sorry, a little nervous, let me start over. I want to make sure I have the same definitions for these things before I get started with my story. A mutex is something which provides mutual exclusion to an object, it's a lock. Most common example would be standard mutex in C++11. A reader-writer lock is a bit different in that it allows one writer in or many readers at the same time. Most common example is standard shared mutex in C++17. We expect higher concurrency when we use a reader-writer lock. In other words, where with a mutex we can allow one thread in at a time, with a reader-writer lock we can have many readers going through at the same time. However, when a writer comes, something different has to happen, and that writer has to be given an opportunity to get the lock eventually. That's what I'm referring to with the read-write preference. Some locks will allow readers to just continuously reacquire the lock. A reader comes in and there's other readers that currently have the lock, they'll just keep getting the lock. This will starve out your writers. That's a read-preferring lock. A write-preferring lock will make, when a reader comes up, he'll say, hey, are there any writers here? If there aren't, it'll continue through and take the lock. And if there are, it'll say, okay, I'm gonna wait for that writer to go through, then all the readers will go through it at once. Something I heard around the office once was that apparently a mutex is all we need. Even though there's a second type of lock, this reader-writer lock, which is supposedly more efficient when you have multiple readers, in practical applications, that's not the case, at least so I was told. I heard that anytime you have a short hold time, which you should have because we're good programmers, and the fact that a reader-writer lock must have some overhead for having this extra flexibility, this extra capabilities, it turns out that the overhead is greater than the improvement in concurrency, and therefore a mutex will tend to be the best and most optimal thing you can use when protecting a data structure, for example. I've heard this we have discussion boards at Bloomberg, so I've seen this in discussion boards. I've seen this on the internet, since being through this. As it turns out, it's very easy to verify. So what sort of started this whole conversation? I was working with someone on a component which basically had a map as part of its data structure. And he had to search through this map, a very short search, but still a little search. And he gave it to me for review, and it had a mutex built into it. I said, no, this can't be the right thing to use. You have readers who can come through and access the thing at the same time, and they should be allowed to do so. Building it with only a mutex allows only one person through at a time, as if I was educating him. He turned around and said, no, you're wrong. He said, it actually works much better with a mutex than with a reader-writer lock. And I was surprised. I said, show me, of course. And he did. I said, well, there's something wrong here. Let's go through your code again. What's wrong here? And we couldn't find it. I was getting a little agitated because, I'm just a kind of New York person. And I said, let's look at your benchmark code. Surely there's something wrong there. And we went through that, and he proved, no, this is good benchmark code. And I said, well, let's look at the implementation of the reader-writer lock we're using. And I looked at it and said, yeah, there's a lot of overhead here. There's a lot of things it's doing which it doesn't need to do. That must be the problem. Surely if we made the reader-writer lock more efficient, this would go away and we'd have the correct implementation. I'm not a quiet person at work. I tend to speak out very vocally, and a peer of mine, another team lead, said, no, I don't think you're right, Jeff. I think you're wrong. Even after you do all this work, it's still not going to be any better. I said, no, you must be kidding me. Come on. We're going to fix this. It's going to be better. We'll prove it. We'll be done. He goes, no, in fact, I'm willing to bet with you, which is odd because he never was willing to bet. And he said, I'll bet with you, Jeff, that you can't make something better than a mutex for this application. I said, you got to be kidding me. I said, it's a pretty long hold time, relatively speaking. Just searching through a short map has got to take a couple of iterations. And I could see where the problem was in my mind. I knew how to fix this. So we bet, and he being a very particular person, he wrote out the bet. It was like 4 pages. Delineated how we're going to evaluate this. He was very Linux-oriented. He was very, used the component we were talking about that started it, and we're going to test over a wide variety of scenarios. But all these scenarios seemed biased to my benefit, so I thought this was an easy win. So I very loudly took the bet, and I was very happy to have it. The only little tricky thing about it was going to be developed by my intern. The intern was excellent. He actually produced an excellent lock, exactly what I wanted. But the reason I bring that up is, again, it was like a 4-page written document. He had a clause in there that after the intern left, I would be able to go in and fix it in case it didn't come out right. But there had to be some limit to that, some time limit. And after that time limit expired, even though I had exactly the lock I wanted to build, I had a pay up for this bet. Fortunately, it wasn't too bad. It was just a lunch at my favorite restaurant, but that's good. So, as I said, I lost the bet. I paid for the bet. It kind of still upset me. Why wasn't I able to build a better reader-writer lock? It would make sense that you should be able to do this, right? I mean, otherwise, why would people have ever thought about them? Why would people want to use them? Surely we get more concurrent than just one thread at a time. So I built a new benchmark to test this, something which gave me more detail, more insight to what was going on. And the benchmark I'm going to be using today, and I will be showing you later a little bit, or showing you results from later a lot, simulates access to a shared data structure. In other words, don't think of this as taking work from a queue. Think of it as getting the work, applying it to some data structure, and going on, doing it as fast as you can, which is a little awkward. You normally wouldn't hit the data structure as fast as you can, right? You wouldn't just get a request, do the work, come back, send it. There'd be some pause. A key thing, I think, to this story is that we're hitting it as fast as we can. It's back-to-back requests. So anyway, you take the next, a thread will come in, it'll work independently. It'll take the next work item. And I say take, I have that in quotes because I mean it's just a counter going up. It does a little bit of math to the counter. It figures out whether it wants that to be read or write work based off a parameter of the program. So it'll lock appropriately, and then it'll do a short little busy loop of work, which was the load parameter I'll be talking about. And again, this load is for when you're holding the lock. There's no delay from when you release the lock to when you try to get it again. And then when you're done, you unlock. And that's what one thread is doing as fast as it can. Overall, these bunch of threads, however many we're running running concurrently, but they'll have a set duration to run. That'll be controlled by a separate thread. In other words, the separate thread will start. They'll set a global atomic to be from 0 to 1. Everyone will be waiting for it to go from 0 to 1. Everyone will start. And then it'll switch it from 1 to 2. And then everyone will be watching for it to go to 1 to 2 to mark when they stop. This was the best way I could come up with to make sure all the threads ran for the same amount of time. And the cost for this, as I'll show later, is actually very trivial. Reading an atomic variable is very efficient. So I'll do this test for some amount of time. I'll repeat the whole thing a bunch of times, maybe 100. Then I'll look at the 80th percentile, and I'll use that as the measurement I'm reporting to you guys. This code is available through GitHub on Bloomberg's public site. Okay, are there any questions so far? Please feel free to interrupt me at any time. It'll be a very short talk if you don't. Okay. So I've actually run this on many, many platforms and many, many setups. Initially, I'd use Bloomberg internal code, it's production code to do this. It's becoming open source. That'll be available to you guys if you want to see it later. I worked on a C++ 11 version, which is what I have posted on that site. I've also done some 17 work to test shared mutex and all that. To be blunt, the first time I wrote this presentation, had all the graphs and all, it was about a 4-hour talk. My wife was very kind to sit through it, but I really didn't think it would be appropriate to put you through all that. So I cut it down, and to do so, I mostly focused on the Linux results, because I thought that would be the most interesting. I will point out 2 outlier results as well, not surprisingly on Sun and on Darwin. But I'll leave further investigation up to you guys if you choose to do so. I think the only platform I really haven't tested on, which is sort of a big hole in my results, is I've never tested it on a Windows platform, which I know is kind of insulting considering what's right across the street. So I apologize for that. I'll get to that eventually and update whenever I have my talk or my paper or whatever. Good to move on. Any questions on how I benchmarked? Going on. Oh, sorry, yes, sir. So the question is, am I changing the percentages of read and writes? For a particular run, for a particular number, it's a constant. And when I show you the graphs, I'll show you a set of graphs from one percentage, then I'll show you a set of graphs from another percentage, and then I'll get kind of annoyingly exhaustive at some point. Which is a very good question, though, because as it turns out, I don't want to jump ahead. when you do all reads versus 90% reads, there's a huge difference in performance. It's a surprising difference in performance, and I'll show that very shortly. Does that answer your question? Anything else? So let me go ahead and manage expectations for a moment. I've already made the joke about my wife sitting through 4 hours, so I can't say that again. I want to be clear that the benchmarks I'm showing you is a very specific usage case. This is not a general purpose usage case. I'm not saying this is going to solve all your problems. I'm just saying if you find that a mutex is generally a good solution for your problem, maybe you should try this reader-writer lock as an alternative. So I'm going to have way too many graphs. I don't know what the count is. I think I have like 40 graphs. To sort of back up my story and to prove my points and to bore you to tears. I'm going to show that synchronization is very expensive. In fact, I'm going to show it's so expensive that it might bring you to tears if this is your daily work. You have to sort of weigh these observations for what they are. This is threads continuously hitting a data structure as fast as they can, which hopefully isn't what you're doing. Hopefully you're not running 16 threads at the same time hitting the same thing at the same. It's just, he's laughing. Are you laughing at me or are you laughing at the concept? That's good, I think. Maybe better than me. I'll of course discuss this implementation the intern gave me, the losing implementation. Again, I want to point out it was perfect, it was exactly what I asked for, and it will be in our production code in the future because it does solve certain usage patterns better than anything else I've seen. The so-called winning implementation. I of course didn't give up with a loss. It's just not my personality. So I'll go through what we came up with at the end and show how it's better. But I will be confirming Mutex is a very good solution in some areas. And it shouldn't be dismissed as a random gossip and made bets over. And in the end, I'll show you something which is a small loss versus using a mutex in some scenarios, but in general, a huge win for these really high contention scenarios. So to start this out, I want to compare two things. I want to show you what the cost of one atomic is versus doing nothing. It actually is doing nothing, which is probably unfair. I should have made it read the memory, but it actually is doing nothing. So to make this more of a reader-writer lock, for this thing I'm calling the atomic lock, which again is not a lock, it's just one atomic access, the lock and unlock will just do a fetch add. They'll increment a value and using acquire release semantics. And the lock shared and the unlock shared will just load the value. So this is much less than you can ever do for a lock, but it clearly just depicts why we have such a problem when comparing ourselves to a mutex. So I left out a whole bunch of things I was supposed to say. Okay, so backing up for a second. I have this load value, which determines how much work it's doing while it's holding the lock. 100 is sort of 100%. It's doing what the load was from the bet. 10,000 would be 100 times that, and 1 would be 100th of that. That's the scale I do. I do 1, 10, 100, 1,000, and 10,000 in the graphs. I hopefully won't be showing you all of them all the time, but sometimes I will. So first graph. I want to point out some things what we're looking for in these graphs before we go through this particular one. We expect as we increase the number of threads doing a particular project that the amount of work we do increases, right? So it should be sloping upwards. Actually, I guess that's the bulk of it. So in this example, I have 100% read. Every access is a read. So for the null, it's doing nothing. And for the atomic, it's doing that atomic load. And we see both of them behave basically the same when this internal delay is very large. And in fact, going to a 90% read set scenario, we still have that behavior when that hold time is very long. Continuing down to 0%. I'm sorry. The y-axis is I apologize. The y-axis is the work. The x-axis is the number of threads. And by work, I mean the amount of work done per second. I actually, as I said, I have that one thread which measures time. It starts and stops everything. It figures out how long it was actually sleeping for, divides the total of the work by that period of time. That gives us the work per second. So this is work per second across the whole system. And you'll notice the values on the y will change pretty dramatically. I'll try to point them out when it does. But from the previous graph, no, they're all about the same. I'm sorry, right, I apologize. I'll point it out later. For very long hold times, the amount of work you're able to do is pretty much constant, which makes sense, right? Most of the work is doing this bogus calculation while I'm holding the lock. There's no effect of the overhead of the lock here. So let's move down to where I do have effect of the overhead of the lock. Here I'm doing still 100% reads. This should be the best scenario. Both, the atomic operation, just the one read, is keeping pace with the do nothing. You can see there is some cost here, but overall, I would almost argue these are relatively the same, in that they increase the amount of work you're able to do the more threads you use. We move one step further to now 90% read, and we see something very different. And this is what I'm trying to point out in this talk, is that even just with a few atomic writes, we see all the scalability disappear. Right? The one going up to the right is the null. That's what we wanted to see. That's where we wanted to remain. When we added that one atomic read, in 1/10 of the work, we immediately lost all concurrency and it went flat. Is that clear? Yes, sir. I'm sorry, can you speak up a little bit for me? I'm sorry, one more time. Oh, there's a speaker here. You should come up here. That's you.
I think it's not quite clear what null means in this context.
Here, null means we're doing actually absolutely nothing. When I call lock shared or unlock shared or lock or unlock, it does nothing. It's inline.
You have implementation of shared lock without any...
Exactly. It is literally doing zero.
Okay.
So it sort of gives you the upper bound of what the machine can possibly do in this benchmarking scenario.
Okay, so you have that implementation in a library?
Yes. Not library, but yeah, in that GitHub repository, it's all there for you.
Okay.
And all it is the four method names and empty declarations. Any other questions at this point? No. Okay. So let's take one more step down this rabbit hole, and we'll go to 0% reads. This is all locks. Now, if you notice, we went from the atomic being able to do about 20,000 work operations per second down to about 18,000. So we do see there's a change in performance here, but it's not dramatic. And most importantly, the character is that it's still not scalable, which we would expect it not to be given the previous graph, but okay. Yes, sir?
I apologize for the interruption.
No, I need the interruptions. Please, more.
So, how many cores do you have?
Depending on the machine I was running it on. This Linux box it was on the slide, it was a 20, does anyone remember? 20?
So, the interesting thing here is between the 20 and 30. So you have 30 threads running on 20 cores. So why would you expect at least any kind of scalability beyond the number of cores?
Good question. I did have hyper-threading, so it might have had more logical cores. Also, to be honest, I had to run it on a shared machine. And while I ran it, in as much a quiet time as possible, it's possible some other people were sneaking on it too.
Right.
But this is not an aggregation, though. This is just the Linux results. So it's a very fair point.
Okay, thank you.
There must have been some other overhead, or it was able to do hyper-threading. Very good question. Thank you, sir. I was supposed to repeat it too. The question was, why do we still see an increase past 20 threads when there was only 20 cores? Yes, sir.
Just continuation to the previous question. So if we're not using atomics, what are the synchronization primitives we are using? Are we using some system calls?
Here at this point in time, I'm just showing you the effect of one atomic operation. So it's not a true lock. I'm going to show you that if we do nothing, performance is here. If we use a lock, if we use just an atomic, we're down here. If we actually use a mutex, we're even way further down here. But you're a little ahead of me. And again, the question was...
My question was, when we compare it with null, saying that we don't use atomic or mutex in that case, and my question is, what are the synchronization primitives we are using on this implementation?
Right, so the question is whether synchronization primitives we'll be using further in the talk, which will be, I'll show you, the next set of slides will be mutex and semaphore. Then after that, we'll go into the losing implementation, and after that, to the winning implementation. Wow, okay, I asked for a lot of questions. I guess I deserve this?
Excuse me. I was wondering if you could repeat what does the load mean? Like, how do you...
So the load was scaled to be so that load is 100, means it was about the same amount of work as the bet. In other terms, it's about 330 or so math operations.
I see. So what are the math operations?
Adds and multiplies. There is one division also. Sorry, there's one modulus which is equivalent to a division. Otherwise, it's about 300 adds and multiplies.
I see. Cool. Thanks.
Sorry, if I supposed to repeat the question and then use the microphone, I don't know. The question was, what is the load equivalent to? Any other questions? Oh, okay. This was in following up on your question. Now we're going to look at the cost of a mutex. But I want to point something out before we start is that I'm no longer comparing it to the null, I'm comparing it to the atomic. So we went from doing nothing to an atomic, now to an actual lock, an actual primitive, mutex or a semaphore. The bottom line is actually an overlay of the mutex and the semaphore. And when I say semaphore, what I mean is that the semaphore initialized with one count, and a lock is a wait, an unlock is a post. Is that good? That's good. So this is 90% read with a very long hold time. This is 90% read with a much shorter hold time. And here we can see what we're expecting to see, but also show the difference between a mutex and a semaphore. So we don't expect a mutex or a semaphore to scale very well, right? They only allow one thread through at a time. We showed the mutex is more efficient than the semaphore. Okay, that's expected too, otherwise why would we have a mutex? We would just have semaphores. And it shows that an atomic operation, a single atomic operation is, 4 or 5 times more efficient, although it doesn't constitute a lock. Any questions here? Sorry, I'm getting over a cold. All right, so let's talk about actual reader-writer locks now and get out of these basic things. What's the design criteria we might have for a reader-writer lock? One would be fairness, and that can be construed in 2 ways for this particular problem. The first sense of fairness when talking about a lock is, as threads come in, do they acquire the lock into you or do they arose there? A second sense of fairness is with regard to readers or writers. When one finishes, do we hand it off to the other or do we allow the same side to keep holding it? I don't know why I keep looking up there. Second design criteria will be the CPU utilization when a thread is blocked on the lock. This is to sort of address the concept of spin locks. Right? If while I'm waiting for the lock, I choose to just keep hitting it, that means I'm using up my whole time slice. I'm using up that CPU. Other work cannot proceed. In general, I'll only be showing you things where we actually suspend the thread, where the operating system suspends you, and other things are allowed to run. Excuse me a moment. It's easy to design a lock where, if we're expecting one operation in a million to be a write, to essentially have it optimized for that. But that doesn't have a real usage scenario. I think just this topic doesn't like me. That's kind of clear. I'm just going to move on from there. So when we built this losing implementation, the goal was to have it have minimal overhead. It was basically a couple of atomic operations and trying to be as efficient as possible. I think I left out some terms from the previous slide. It was writer preferring. In other words, when a reader came in, if there was writers waiting, it would block. It wouldn't allow that reader to get the lock no matter what happened. This is important to prevent starvation of your writers. And when a writer unlocks the lock, it prefers to give access to readers. So the goal of this was to try to alternate. You have a writer go, have a bunch of readers go, have a writer go, have a bunch of readers go. Sorry. And to address priority inversion, which is something I was supposed to talk about before, we wanted to use a primitive to select the next writer. Priority inversion is important because you could end up having a very high priority thread waiting for a low priority thread to do work. Most operating systems give you some, give you some ability to adjust the priority of your threads coming out of the lock to have the highest priority of itself or threads waiting on that lock. Does that make sense? Too fast? I see one nod. A lot of blank faces. Okay. We want to get that ability if we can. In other words, using an atomic for waiting would probably be bad for us in that sense. So I'll give pseudocode next, but basically the state of this machine is that it tracks the number of readers, it tracks the number of pending readers, readers who are waiting for writers for the next writer to go, and writers, both whether there's an active writer and any pending writers there might be. And it uses one semaphore to block writers and one semaphore to block readers as needed. So what do the four methods look like? The lock, which is the mutual exclusion lock, increases the count of writers. If there are any readers or other writers, it waits on the semaphore. So this is a thread coming in saying lock. We'll follow that procedure. And for unlock, it'll decrement the count of writers and move all the pending readers into a reading state. It'll also post that semaphore, which is blocking those pending readers, so let all of them go through. And otherwise, if there's no other readers, it'll go ahead and allow the next writer to go through. Does that make sense? So basically, it shifts off to the readers if it can, or it goes over to another writer. On the other side, on the shared side, a reader will come in, and if there's no writers, it'll just increase the count of readers and go on with its life. Go ahead and do whatever it has to do. If there are writers, it'll join the pending readers. It'll wait. It'll wait on a semaphore. And on the unlock side, it decrements the count of readers. And if this was the last reader and there are writers, I have to tell the next writer to go. So I post that semaphore. I know it's a little quick. If you need to get more detail, you can check out the GitHub or talk to me later. Let me go ahead and show some results for this. Oh, good, my smiley face shows up. So I added these two arrows to all the graphs from this point forward because there's other information on this graph which isn't the primary reference point of what I'm talking to. So one will point to the mutex, which will be our reference, and here is the bottom blue line. And one will be the losing implementation, which is the top purple line in this graph. The third one is the pthread implementation of a reader-writer lock. It is biased towards readers when used right out of the box, and that's how this is. In other words, if readers currently have the lock and other readers come in, they'll just go through. They won't wait for writers. It supposedly gives you better concurrency. That's how I allowed it to run. Also, I'm giving you my opinion of the graph with regard to whether we're beating mutex or losing to mutex. I hope there isn't a legend needed for that. Is that clear? Okay. So here we are at 100% reads and very long hold time for the lock. Again, a ridiculously long hold time for most applications. And we see that our reader-writer lock, as expected, is outperforming a mutex. So this is a good slide for us. Here I decreased the hold time of the lock by a factor of 10. We start seeing a little more shape to it. It's still interesting, but still scalable. As we increase the number of threads, we get more work done. This is, again, a good slide. Here's where things get a little more interesting. At the scale of work we were doing for the bet, we see that it's not a very scalable process. This atomic operation-based reader-writer lock plateaus. It doesn't have as much scalable as we would want. We're still outperforming mutex, which is great, but it's really not giving us what we had hoped for, or what we would have expected before we started this process. Yeah, I locked the doors. I don't know how he got out. But again, still, it's a good win for the reader-writer lock. And I'll just show you two more graphs which basically show the same thing. Decreasing the hold time of the lock changes the graph, but still basically the same result. And again, but here they're much closer. So I give that neutral face. So to recap so far, for exclusive reading, we did well. This losing implementation did well when we're doing 100% read work. And we crushed the mutex when the hold times were very long, which was expected as well. So let's move on to when we have only 90% read, when we have some write work done in this workload. This first one, again, is a very long hold time, so we expect the reader-writer lock to perform very well, and it does. Moving down by a factor of 10, something odd happens. The performance of this losing implementation is now actually losing at the higher concurrency levels. But let's keep moving. At the level of the bet, we see a strong loss of this reader-writer lock compared to mutex. Even though it's 90% reads, we're still not as efficient as mutex here. Not much else to say. It was very shocking to me. I don't see you guys weeping or anything, but I certainly was. Just moving down this path, showing even more badness. And at just if I hold the lock for just a few math operations, this is the graph I have at 90% read. Again, it's showing that this losing reader-writer lock, even though it's 90% read, can't outperform a mutex. So to recap the 90% reads, Mutex was generally better. Only with a very long hold time did the reader-writer locks outperform. This is not what we want. So let's change the go ahead, yes. How is it possible what? It's not zero, it's just scaling. It's actually probably around, I don't know. I'll have to look at the actual numbers. It's probably around, no. It has to be around 300, I think, if I remember correctly. Yeah. So what we want to do is we want to minimize the loss to the mutex in scenarios where a mutex is conceivably a good thing to use. In other words, in unfavorable conditions for a reader-writer lock. But we want to outperform the mutex when we're doing primarily reading. That makes just logical sense. That's what a reader-writer lock is for. And we really want to crush the mutex when we're going to hold the lock for long periods of time and doing primarily reading. So as an example of let's join them, if we can't beat them, let's join them. We're basically going to build something which is a mutex plus a little bit of other machinery to try to outperform the mutex. So I'm kind of in a chicken and egg position, chicken and the egg situation, which came first. I want to tell you a little bit about the lock, but I don't want to tell you too much yet. As it turns out, what really made this lock implementation work well was the ability for a thread to reacquire the lock. In other words, I come in, I get the lock, I do my work, I'm then able to reacquire the lock again as quickly as possible. Whether I was reading or writing, and whether I'm going to be doing reading or writing, this ability to reacquire that lock was very important. That's where we got the efficiency from. Having said that, it's going to be kind of designed as, on the lock side, you can imagine being just a mutex. I come into the lock, I get the mutex, I'm done with the lock, I release the mutex. On the read side, I'm going to lock it and release it on the lock shared operation. Obviously, there has to be some other machinery involved now to keep everything kosher, so to speak. That's basically the idea. And as such, since I'm using basically this as one mutex, it's not going to be reader preferring, because readers will not be able to acquire the lock when other readers have it, nor will it be write preferring, because when a reader comes in, it won't check to see if there are writers. It'll still try to get that mutex lock first. Technically not true, but it gives you the right concept. And I want to use this mutex to select the next reader-writer to handle priority inversion and whatever other concerns I might have for performance. One thing I have to mention, though, is it's explicitly neither reader preferring nor writer preferring. So at some point, someone may say, well, what is it doing? What is it experimentally doing? And one would expect, since I'm using basically just a mutex, all the readers and writers come in. If they're 50% one type, 50% the other, I would get out of it, with equal probability who the next user is, a reader or a writer. Experimentally, it seems to prefer writers a little bit more than that, but perhaps not statistically significant. The basic state of this is I'm going to track the number of active readers, the number of pending writers, and whether or not there is an active writer in an atomic state. There'll be a mutex which every thread which comes in will essentially access. And if I'm a writer and I come in and I get the mutex, I'm then going to go to a semaphore. This is in reverse of a really well-known old implementation where the semaphore came first. But let's just move on. Oh, one thing to note here. Since the writer that comes in gets the mutex and then may have to wait on the semaphore, it's only going to wait on the semaphore if there's readers currently accessing the lock. As such, it's possible that we may have an interesting performance issue when there are a low number of readers. In other words, the lock may perform better when there's 0% readers and worse when there's 10% readers. So we'll test for that. So the pseudocode is, again, on the lock side, increase the number of pending writers. Every writer that comes in is presumed to be pending. Lock the mutex. Switch the writer from a pending to an active writer in the counts. And if there's any readers, wait on a semaphore. And unlock is just to erase the indicator of the writer and unlock the mutex. On the reading side, we do have to do a short circuit, an atomic short circuit for if there are no writers or pending writers and I'm a reader, just go ahead and take the lock. That causes, without that, you have a big performance drain. And as I said before, you're going to lock the mutex, increase the number of readers, unlock the mutex, all in the lock shared. And the unlock shared, you'll decrement the number of readers. And if this was the last reader and there is a writer, post that semaphore, release that trapped writer. It's a very simple implementation. If you look at the code in that GitHub, you'll see they're all like 5-8 lines of code. Very straightforward. So let's start on the easy path. Again, a very long hold time, all read workload. We're comparing, on the bottom is the mutex, which we expect to have no scalability and to kind of not do well on this workload. And the top is this winning reader-writer lock. For reference, I include the other two reader-writer locks from previous slides. They don't have arrows next to them, and they're both on that second line at the moment, but the pthread implementation and the losing implementation will be shown as well. So this is good, but very expected. It's a very easy workload for the reader-writer lock. Decreasing the hold time of the lock to something still long. We still see good scalability and good performance. Moving to slightly more interesting, at the workload of the bet, we see that same shape as before, of course. Well, not of course, but we do see the same shape as before. But we still see a very strong win for the reader-writer lock. Decreasing again, we still see a win for the reader-writer lock, and going to a trivial workload, they all kind of tie out. So let's move to a 90% read now and see if we can do better than before. So on this ridiculously long hold time, we are outperforming the mutex. However, we're not the best on the graph, and that's fine. But we are outperforming the mutex. Moving down towards more reasonably sized workloads, we have this graph where essentially a mutex and this new implementation are doing the same. One step further, this is the workload of the bet. We see that this new implementation is outperforming the mutex quite handily, whereas the previous one, the one the intern did, is the bottom graph, or the bottom curve, excuse me. So we can see things have changed here dramatically from previous implementation. Going to a very short hold time, we still see the new implementation winning, and going to a ridiculously short hold time for 90% read work, we show the new implementation beating the mutex quite handily still. So this is sort of good results. I could sort of end here. But let's go further and check out the other side. When we have 0% reads. In other words, this is what a mutex should be good at. These numbers are all basically the same. This graph has no meaning. I don't know if you can see the scaling. It's basically between like 16 and 17 for amount of work done, so it's not really useful. Scaling back to a long hold time, but not crazy. Again, this is where 0% read, so it's all write work. This is what a mutex should be optimal out. We see this new implementation and the mutex being basically the same. Going down to the workload of the bet, we still see them being the same, even though it's all write work. And finally, at short hold times, we see mutex starting to edge out this new implementation. And then at a ridiculously short, few math operations, you see the mutex outperforming this reader-writer lock. But again, it really should, right? Because we're really just the mutex plus overhead. We should be losing in this scenario. So as I mentioned before, we have that semaphore inside the mutex for the writers, which is only used when there are readers present. So that can cause a negative effect when there are a few number of readers. So let's just go through and check that real quick. So the 10% read load, a very, very long hold time, not much difference between the lock implementations. Moving down to still long hold time, not much difference in the implementations. Again, this is not much difference between mutex and reader-writer lock. The losing one is substantially worse. At the load of the bet, we see the new lock outperforming a mutex. In other words, it's able to capitalize on that 10% of reads versus 0% reads. It's not a cost, it's a benefit. And the same goes as we reduce the workload again. And down to the shortest possible workload I can do, which is just a few math operations, the mutex and the new implementation are basically the same. So to do a Linux recap, to recap those last 20 slides, in all those scenarios, there was one time mutex significantly outperformed this new implementation. There's one time mutex slightly outperformed it. Did I read that right? Significantly outperformed and slightly outperformed. 8 times where the two were kind of tied. And 10 times where this new implementation was substantially better than the mutex. If we focus now just on the work we expect the reader-writer lock to be good at, those 10 slides that we did initially, the 100% read and 90% read, there were 2 ties and 8 times where the new implementation was significantly better than the mutex. I wrote it from the other direction for some reason. Is that pretty clear as a win, I hope? I think so. I want to show you two other platforms real quick. Again, I tested on many platforms. I tested with different versions of the code. One platform which was consistently bad for me was Sun. To start off, I'm showing you just on Sun what a mutex and a semaphore look like on these graphs for the whole time of the bet, a workload of a few hundred math operations. A mutex outperforms a semaphore. With 100% read on a same workload, all the read-write locks outperform the mutex on Sun. Unfortunately, when you go down to 90% read, you can't beat the mutex on Sun. I'm not sure why this is the case. It's obviously something specific to Sun. Our IBM machines and Macs and whatnot all perform as I want them to. But I felt that this was one of the two aberrations I had to show you. The second aberration was on this particular Mac machine. Here I'm showing you the performance of a mutex versus a semaphore. And here you notice the semaphore is much better than the mutex, which seems odd. And again, the semaphore implementation is it starts with a count of 1, and it waits or posts as it's locking or unlocking. So since semaphore is more efficient than mutex here, I switched my implementation to use the semaphore as opposed to a mutex. And then goodness came out of it. We see that 100% reads, the new implementation handily beats the semaphore. And at 90% reads, we have the same scenario. So in summary, I hope I've showed that synchronization is very expensive. Doing anything, even just one write atomic operation, will drastically affect your scalability. Mutexes are pretty good in these scenarios, these high contention scenarios where there's low hold times, but we can do better than the mutex. Are there any questions? I guess we got them all out during the talk. Very good. Thank you very much for your time.